All right, we're going to talk about moles. And so if you ask a group of people who took chemistry in high school to write down 5 words they remember, it's very often the case that moles will be on everyone's list. Okay. Sadly, that does not always mean that everybody walks away from high school chemistry understanding what a mole is. And so in the next few minutes, we're going to do our best to clear that up for you and make sure you have a good grip on this idea because it's going to be with us throughout the semester. All right. So moles are all about counting molecules. Chemists like molecules. You've already heard me say that a number of times. And so we very often, not too surprisingly, want to know how many molecules we're talking about, right? That's the way we keep score of quantities, is by how many molecules is that. Molecules, by definition, are really small. And so if I have a macroscopic amount of stuff, I have a really lot of molecules, like numbers with exponents 10 to the 20th, 10 to the 30th power, things like that. All right, it's not that hard to get to have that many molecules. In order to do this, then, if we're going to count the molecules, we're going to need to count them by some sort of large quantity. All right, gosh, we like to say this is the same as when people sell paper. They decided a long time ago they didn't want you to just say, I want to buy 723 sheets of paper, right? They picked a number, they said that's a ream of paper, and you buy it that way. Okay, same argument. Okay, chemists picked a number to say, how are we going to count the molecules? Okay, the number is a little bit peculiar looking, but it actually makes sense how it got to be that way. So a mole is a unit of quantity, right? Think of it as being equivalent to a dozen, say, or anything like that, right? Just another way of counting things. And so 1 mole is equal to that number there of things, 6.022 and change times 10 to the 23rd power. That number has a name, which you may remember from the past. That's called Avogadros number, okay? Until quite recently, we used to say Avogadro's number was an experimentally determined quantity. That is actually no longer true. This is something that's mostly of interest to serious measurement geeks, I guess. But as of 2018, that number is now an exact number, meaning what is written on the screen right there, that is the exact value of Avogadro's number. That many things is a mole. Okay, that's all Avogadro's number means. So anytime I have that number of things, whatever the things might be, it's a mole of them. Okay, and that's how I want you to think about it, right? We will, 6.02, 6.022. That's enough digits for the vast majority of problems, right? If I'm calculating something where all the other numbers in my problem really have a lot of digits in them, then I might actually look up the rest of the decimal places. But I confess 6.022 is as far into that as I actually remember, and just know to write down if I'm doing a problem. Right. So that's Avogadro's number. That's what a mole is that many things. This is a picture that's actually in your textbook, but it's moles of some different elements, right? Gosh, in live class, we have this box of things that's just moles of different things that I sometimes bring into class and hold them up, but I did not go and try and swipe the box and bring it home or anything like that. And so we'll use the picture, right? You can see that if you look at those samples, the way they're listed on the right, bromine, aluminum, mercury, that's starting with bromine is the one in the tall flask there, which is kind of a reddish orangish vapor up above a liquid of the same color, and then they go clockwise from there, right? So from bromine we go to that large ball of aluminum foil, flask with some mercury in it, a piece of copper tubing, some iron nails, a little bit of zinc, which looks like it's recently been melted from the appearance of it, and some sulfur there sitting on the black surface at the bottom left, right? If you look up the atomic weights of all those things, they're all different, right? If you look at them, they're all different volumes. If you could pick them up, you would know that you'd notice right away that the mercury is a lot heavier than the aluminum, for example, right? And that's certainly true. Okay, but all those things, what they have in common is that they have Avogadro's number of particles in them. Okay, there's one thing a little bit weird going on here, and that is that all but one of those is a mole of atoms, meaning it's Avogadro's number of atoms. The bromine over there should actually be a mole of bromine molecules because bromine happens to be Br2. Okay, so I'm going to use that to illustrate a somewhat peculiar and sometimes confusing point about moles. Okay, if I think of that as being a mole of bromine molecules, that means I have Avogadros number 6 times 10 to the 23rd power of bromine molecules. Right, each bromine molecule. So if I have 1 mole of Br2, we use MOL. I can't talk, it seems, today. We use MOL for an abbreviation for mole, which saves us 1 whole letter, I guess. But in 1 mole of bromine, Br2, I could say that contains, and this part will bother some of you, that contains 2 moles of bromine atoms. Okay, and it deeply troubles some people that I can say this is a mole and it's got 2 moles in it. All right, think about this as saying that, gosh, right now in my garage, there are 2 cars in there, and they very definitely have 8 wheels between them, right? And so I have more parts than I have whole things. In this case, the BR2 is the whole thing. I've got Avogadro's number of BR2s, right? Because each BR2 contains 2 BRs, that says I've got twice as many of those. If I had a mole of water, I'd be able to say my 1 mole of water contains 2 moles of hydrogen atoms and 1 mole of oxygen atoms. Or if I wanted to get really crazy, I could say it contains 3 moles of atoms altogether, right? If I no longer cared what kind of atoms they were, I could say there were 3 moles of atoms all told in 1 mole of water. All right. It's important that you get used to those ideas, because otherwise they'll really, really get you just thinking about things in all kinds of wrong ways. Okay. So try to wrap your head around having that make sense. Like I say, it helps for me to just think about it as saying it depends on whether I'm counting like big things or the pieces they're made out of. If I'm counting the whole things, then I have 1 number. If I'm counting pieces, then I very often would have more pieces than I have whole things. Right, and that way it seems, at least to me, to make some sense. All right, so Avogadro's number was the reason why Avogadro's number is that somewhat strange-looking thing, and not just a nice an even power of 10, say. Since we said it's now a defined quantity, we could have called it anything, right? The reason it's not is it was originally set by saying we wanted to have the atomic weights in AMUs and the what we'll call molar masses, or the masses of a mole in grams, be the same number. Okay. And in order to do that, because the gram was already defined, right, that said that we just had to figure out how many carbon-12 atoms it took to add up to 12 grams. And that was how a mole used to be determined, right? Why is this important? It means the mass of 1 atom or molecule in AMUs is the same numerically as the mass of a mole of them in grams. All right. So if I look up carbon in the periodic table, we'll know that carbon, the atomic weight is 12.011 AMUs. That's an atom. And that means that a mole of carbon should be 12.011 grams. That would be a mole, right? And that factors in the isotopes that we talked about and things like that, right? That's why it's not exactly 12, because some of my carbon atoms, if I have Avogadro's number of them, I'm going to have 1% of them be carbon 13. That's going to make my mole a little bit heavier than the 12 grams that it says on the top. All right, that's important for convenience, because otherwise it would be really awkward if we had to have 2 different lists of masses, right? One for being in AMUs and one for being in grams. That would be silly, right? And so that's why, because we wanted to keep those numbers the same, that's why Avogadro's number doesn't get to be a nice round number that would be easier to remember and in some ways to work with. Right, so a lot of problems that you'll do in the next week or 2 in this class involve converting between mass, moles, numbers of molecules, things like that. All right, these are unit conversions. Okay, there's a reason why in the very first live class session I started with some unit conversion problems, right? And that's because there's lots of things we do in chemistry that, although they don't always seem that way to students, they amount to converting units. And this is these are some of them. Okay, so if you believe in your core that you can convert units, then you should believe that you can convert mass to moles, grams to moles, moles to molecules, grams to molecules. Any of those things you can do just by keeping track of units, right? These are all just different ways of describing how much stuff we're talking about. The things you're generally going to use to work with here are going to be atomic or molecular weights. That's just grams or AMUs per atom or grams per mole, things like that. Densities maybe, because if you have density, density is mass over volume. So if you have density and volume, that gets you a mass, right? And so that's another route to get there, things like that. And if you just keep track of the units and say, I'm going to start off by saying, what's the thing I know? This tells me how much stuff I have. I can turn that into any other kind of unit I want. Okay, it's really good if you can just get yourself convinced that this is something you can do, because this is something you can all do if you just think about it in the right way. All right, so we're going to do our first mass to moles to number of, in this case, atoms, I guess, calculation. It's an inherently a little bit silly one, I confess. I am going to calculate how many iron atoms and how many moles of iron are in this skillet that we're looking at there, okay? That is just a picture of a cast iron frying pan, a 12-inch cast iron skillet. It says weighs about 8.4 pounds. I confess I'm the sort of person who actually looked that up on a cooking store website to get a number to put in there for this, right? Picked a cast iron skillet because it is actually literally true that pretty much every atom in that cast iron skillet is iron. Okay, so I wanted something that was just a pure one-element substance, and that's what I picked. We're going to find out how many moles that is and how many atoms that is, all right? If it's been a couple of years since you took high school chemistry and being confronted by the word moles again is just making you tremble, don't be alarmed. Let's just think about how we're going to do this, right? The thing I know is that I know I have 8.4 pounds of iron, right? The other thing I know is that I have available the periodic table, right? So the periodic table, or just a listing, that'll tell me the atomic weight of iron. Okay, and that number happens to be equal to 55.8. We could look that up. If we were actually in a chemistry classroom, instead of in this room in my house, I'd be able to just point to the wall and say, look on the periodic table over there, and that would tell us what the atomic weight was, okay? And that thing, one way to describe that thing is to say this, we're gonna give this units, we're gonna call this a different name now. We're gonna call it the molar mass, which sounds fancier. And that says it's 55.8 grams per mole, meaning 55.8 grams of iron is equal to 1 mole, okay? So my plan for this problem, and a lot of you are just looking at this saying like, oh, just do the problem already, right? But not everyone is there, so we're gonna make sure we take our time going through this. So we're gonna go from pounds. Pounds are not units we usually do science in, so we're gonna first go from pounds to grams. I happen to know that conversion factor. If I didn't, or if you didn't, you could surely look it up. Then we're going to go from grams to moles. And for the part that said from atoms, we're going to go from moles to atoms. Right? And each one of those things is a conversion factor. Right? The first one says that 454 grams is equal to 1 pound. This one, the grams to moles one, that's the molar mass that I wrote up there. And this one is going to be Avogadros number, because that's the conversion between moles and atoms, okay? So that's the game plan for our problem. Let's just go ahead and do the numbers. All right, we start with the thing we know. We always start with the thing we know. And the thing I know is that I want to start from 8.4 pounds of iron. I want to convert them into grams. And I just said that 1 pound of iron, 1 pound of anything really, is equal to about 454 grams. Okay. And then now I'm in grams of iron. I'm going to keep putting iron on there just because it's a good habit. Soon we'll get to be doing problems where we have moles of different things floating around in them. And if you get to be labeling stuff as grams of this stuff or moles of that stuff, it'll help you avoid some chances to mess up. If I stopped there, I would be at grams of iron. Obviously, I would have a much bigger number than my 8.4 because grams are little. I'm not going to stop there. I'm going to keep going. I'm going to say that I know that 55.8 grams of iron, this is my atomic weight that I mentioned, is equal to 1 mole of iron. Okay, that's one of the things I said I was going to calculate, so I'll write an answer here that says that's about 68 moles of iron. So if anybody asks you how many moles are in a frying pan now, you're ready to answer that question, okay? We know that, just to check, the pounds go away, the grams go away. I'm left with moles, that's good. If I wanted to get to atoms, that was the second piece of my question, 68 moles of iron. I know that 1 mole of iron is just written as Fe for its formula, so that just says that I have Avogadros number here. And if I multiply that out, I get 4.1 times 10 to the 25th iron atoms. Okay. I'm trying hard to encourage you to do a check for reasonableness. On the moles part, there's no way that I expect me or you or anyone to know how many moles ought to be in a frying pan. You could just look at the numbers, I guess, and say the 450 over 55, that's somewhere between 8 and 9, right? And so when I multiply 8 by something between 8 and 9, I get a number around 68, so that makes sense. On the atoms one, the simplest check is just, did I get a really huge number, right? I'm finding out how many atoms are in something that weighs 8 pounds. It's got to be a giant number. And in fact, I do get a giant number over there, 10 to the 25th power, right? That's a particularly good check because one thing that students do often, particularly if you're the kind of person who just types things right into the calculator, doesn't ever write down or think about units, is you get to this step and you say, I know I need to do Avogadro's number, right? But then if you divide by Avogadro's number instead of multiplying by it, then your answer is actually off by a very large amount, right? 10 to the 47th power or something like that, which is enough to make a big difference in just about anything worth calculating, okay? So if you're calculating a number of atoms or of molecules and you get a number that's smaller than 1, then you just know that that can't be right. And you should set about finding and fixing the problem then. All right, one other quick and simple thing for this segment, and that's just getting the molar mass of molecules so that we can do the mass to moles conversion for molecules and not just for atoms or elements, okay? Like I said, I deliberately picked that frying pan there because it was a thing I could think of that was made entirely of one element, okay? But molecules have molar masses as well. They just don't show up in the periodic table directly, right? We can still get them. All we have to do is use the atomic weights of the atoms, the molar masses of the atoms, and multiply them atom together, right? So if I wanted to get water, my formula tells me it's H2O. That says I have 2 hydrogens and 1 oxygen in every molecule, okay? And so that just says this one, the 1.0079, since I'm carrying around all the decimal places here apparently, and this version for oxygen, I multiply this one by 2, where that 2 comes straight from that 2 up there. This one, the 1, comes from the fact that there's not a subscript on the oxygen, right? Multiply those out, add them up, and I get this number over here, 18.01, whatever, okay? Students often, if we were in class, somebody right now would be raising their hand and saying, like, do we have to use all those decimal places all the time? And my answer would be no, that would be silly in most cases, right? That number 18.01, right? That's 18.0 to at least 3 significant digits. So unless I have a problem where I have more than 3 significant digits in all of the other numbers, all the measured numbers, then it doesn't do me any good whatsoever to have carried around those decimal places, okay? And so for most of our purposes, for the elements whose masses are very close to whole numbers like those are, then it's going to make sense to just use the whole number equivalents in the vast majority of cases. I will tell you one category of problems we'll do soon where I actually like to use the decimal places, all right? There are some elements, like if you look up chlorine, the atomic weight of chlorine is 35.45. Okay, that's a bad one to round to a whole number, right? Because it's pretty much splat in the middle. And so there I would just be using that number because I wouldn't want to make that big of a shift in things by doing that, okay? So just try to use a little bit of judgment about that. And particularly if you're taking a test and you actually, are under on a timer, if you just know that you can put in 1 for hydrogen, that'll save you some time versus having to flip to the periodic table to look up the 0.0079 piece, okay? I'm going to do a quick example of something a little bit more complicated than water. This is the molecule whose formula we sorted out in the previous video, right? So we got C12H12O4 for that, for its molar mass, for its formula. Now we're going to find the molar mass, okay? So this is, I'm just giving myself a little room to write, okay? So if I look up the atomic weights for these things, carbon is 12, hydrogen we're going to use 1. I'm just going to use whole numbers for them all. Oxygen is 16. These are all super close to being whole numbers anyway, okay? And the way I'm going to do this is I'm going to just say, I'm going to be quite systematic about it. I'm going to say for the carbons, I have 12 of those, and each one is 12 grams per mole. Okay, so that says I have 144 grams of carbon in 1 mole of my compound. For my hydrogens, I have 12 of them times 1. So that says I have 12 grams of hydrogen in there. For the oxygens, I have 4 of those, and they are 16 grams per mole. So I multiply that out, and I get 64 grams of oxygen in there, right? If I take all those and add them up, I get, what do I get? I get 220. Yeah, that's what I get. Okay, so that says I have 220 grams per mole for that compound. All right, so this then is the molar mass of this compound from the formula. All right, so you can see the arithmetic there is simple, right? All we're doing is some very straightforward multiplication and addition. Just make sure we have the things in place. That's how you find the molar mass of a compound. Once we have that number, if I wanted to know how many moles were in some number of grams or some number of pounds or some number of tons or whatever, some mass of that substance, I'd be equipped to do it, because that 220 grams per mole, that's my conversion factor, whether I'm going from grams to moles or from moles to grams. Right? That thing works just like saying there's 2.54 centimeters in an inch. I can use it in either direction, right? I just want to make sure that I stack up my units in my calculations so that they all sort themselves out when we're going through things.